we'll get to the part where I think that, to me, all the other stuff is neat, but if you don't know what to do with it and how to do it in the right manner, then I've really wasted my time today. So what I want you guys to be able to do at the end of all this is to be able to V-rot like a champion, because this is the whole idea, is can you apply this stuff properly? We've already hit on it, but I want to show you the pitfalls, the real world problems that you run into. You know, you're going to go look at radar probably tomorrow and say, wait a minute, this guy showed me this Louisville tornado, everything lined up, it looked all super easy, and where's that signature today? Well, fortunately for the people in the United States, we don't have violent tornadoes every day, everywhere. So most of them are going to be quite a bit messier. Point here is that data quality plays a huge role in proper interpretation and application of this information. So you got to be able to say, do I trust the data? And when we say trust the data, you want to make sure that it's a meteorological scatterer resulting in the velocity data. Bugs are not meteorological. You know, the velocity returns from dragonflies, while they might mean something, that's not what we're looking for. So you're looking for precipitation that is driving the power return to the radar. And so again, it's not always the case that you don't always have meteorological scatterers. And then you get these artifacts, and the interesting thing is they're very common in the inflow region of right-moving supercells, which is exactly where you're going to be looking, and if you're not paying close attention, you can easily misinterpret. So again, how do we identify these things? And an even better way to approach this is don't be the only person that looks at it. If you're just doing it for your own amusement, fine. You don't have to literally call your mom and have her interrogate the radar just to see if you're interpreting it properly. But if you're doing this for real, it's best to have someone else look at it and make sure, hey, do you see this the same way I do? Okay, so here's an example from southwest Oklahoma, right-moving supercell, or it's actually northwest Texas, sorry. This one, so we're looking at a storm, and we're just moving forward, and you see, and then we go up in elevation, so there's some circulation. Again, so the question is, how much of this is real? And is there anything that stands out as odd looking in the velocity data? You notice this rather abrupt transition? Well, let's take a look at what that means. And that's where all the strong inbounds are. Okay, so we continue, we'll look at the circulation. You would get, oh, well, it's moderate rotational velocity, 55 on 20, VROT in the 30 to 39 range. So there's some probability of a tornado. It's not real high, but at least something worth considering. But how do you identify the tornado potential with this kind of storm? This is where the other variables, dual pole variables, come in. So when we highlight this area, this is another one that we haven't talked about yet, spectrum width. This talks about the variance of the velocities within the velocity gates. How much variability is there? Now, in the neighborhood of tornadoes, it's very high variance. I mean, that's not a shock. But what about this huge area with all this variability? That's also where the correlation coefficient is low. Oh, well, it's a debris signature, right? Uh-oh. Now some of the weirdness in my velocities are starting to become apparent. Like, wait a minute, why do these strong inbounds here line up with this highly variable velocity signature that looks like it's non-meteorological? Oh, that's also the low reflectivity inflow region of the supercell. So if you were just to throw that out there, you know, it's too bad for you. The point here is that that's side lobe contamination. It is a reflection of the reflectivity aloft. Projected is overwhelming. The piddly reflectivity along the main beam is being overwhelmed by the side lobe, really high reflectivity aloft. Doesn't just happen in Oklahoma. This is Nevada, if anybody knows where LRX is. You have to do a lot of this to remember all these 88D sites. So this is looking to the south of the Elko, Nevada radar. And this is at night in July in Nevada. It does happen. So we're going to look at the storm. So we're going up. We see, well, it looks like there's vertical continuity. Question is, what's our potential with this storm when we consider everything? Again, rotational velocity similar to the other case in the mid-30s. Is there tornado potential? Now, you know from the climatological maps, there weren't a whole lot west of the Front Range of the Rockies. So, and you could say it's Nevada, and the chances are it's going to miss anything anyway. I mean, you can do this and probably get away with it, but you're not going to be employed as a meteorologist very long, certainly not in the ELCO office if that's the kind of argument you use. So the question here is, what about the velocity quality? Is there something that looks a little unusual about the inbound velocity signature here? Well, we can look at other things. ZDR, this one, in this case, we're talking about, is it size sorting with raindrops and other things? And then we've also got the CC. So if you look at, there's a signal here where that noisy signature in ZDR, just another way to look at it, is not necessarily reflective of a meteorological target. And by the same token, it's low correlation coefficient, which is also right where the strongest inbound velocities lie, which is out in the inflow region of the storm. Relatively weak reflectivity. Again, you'll have to credit one of your previous classmates, Joey Pica. He's the one that put the humor in here. I'm just going with it. Okay, so we look aloft, and we'll compare the storm. This is going up to 2.4 degree elevation. You notice that in the inflow region, that's high reflectivity aloft. I mentioned the side lobe contamination. What it is, it's the strong, notice this smoother velocity signal aloft. That looks more realistic. You have gradual transition to a max and gradual transitions out of it, whereas this stands out in a different way. But you notice the outbound velocities have a smoother appearance. That's where the reflectivity is. So this one is once you get used to looking for this, you could immediately say, wait a minute, these inbound velocities are questionable. And anytime you're looking in the inflow region of a supercell and you don't have a high reflectivity appendage, make sure that you're looking where the reflectivity lies. Okay, so now what? It depends, the velocity quality depends on the relative contributions of what's returning power to the radar. I've already touched on it a little bit. And we just want precipitation particles to dominate. So the idea here is we're going to pick, we're looking at some velocities in this little box. And the idea here is that some part of this signal is coming from meteorological targets that is producing inbounds, but there also can be outbounds, and they're the ones you don't want. So the question is, what's the relative frequency of these two contributions? And so we slap it on here and say, okay, if we have inbound, which would be high reflectivity, that means the meteorological targets are dominating the return, higher correlation coefficient. Again, in the absence of lofted debris, rain looks fairly consistent, and you'll have smooth data. That gives you confidence that that is a meteorological return and that it's something you can trust. Now, if you're over here, you have lower reflectivity, low CC, and this, it's hard to define it, but the speckly look, very sharp, unnatural looking gradients, that's usually a sign that it's non-meteorological. And then sometimes you get where it's going to be very difficult to tell. I mean, there's sometimes where you just can't say for sure. And as I've mentioned with the other stuff, this is where your understanding of the environment and storm structure should tell you what should I expect in the first place. You get one of these odd velocity signatures, again, at 9 or 10 o'clock local time in Nevada in July. Tornado's not the first thing you're probably thinking. So the question is, look at the environment, does it make sense? Now, it's entirely possible that it does make sense and that maybe it is a tornado risk. Okay, so now what? You've got to look at the data have to look right. You've got to look at as many variables as necessary to convince yourself, and then get as many people looking at the data as you can, because these processes are very difficult to automate. I mean, people are working on ways to do it, but there's the hydrometeor classification algorithm, dual pole. It's pretty good. It would be potentially one of those things you could use. Say, hey, if it says it's rain or something like that, I can trust this more. If it gives you, it says it's bugs, maybe I don't believe this velocity signature as much. So again, and then there are other things here. We've got a VROT of 52. Would anyone question this one? Oh, I see. It's a supercell. I see a debris signature. I see strong rotation. Even that normalized rotation thing and GR shows up. Is there anything odd about the signature? First of all, we have some quality control problems with the velocity data, the dropouts. A lot of that signal is in weak reflectivity. You continue, look at the character of the velocity data just from one scan to the next. Not very consistent, is it? That's not a realistic. Now, if you just plug these numbers in, these are SIGTOR values. You're going, oh, well, I'm sure there's a damaging tornado just grinding away right here. The problem is you keep going and it keeps showing this. The only tornado was actually this. Notice now it's in the reflectivity appendage. It's got the high reflectivity, and there's a little bitty CC min. So of all that other stuff, you could be looking back and saying, wow, I suspect that it's, you know, this devastating tornado. And the point is the tornado was right there. So all the other stuff now, you could say, well, who cares? This storm went on to produce a tornado. Point is you'll find storms like that won't. And this is one way to cut down false alarm. And it takes you using your meteorological toolbox and your skills as a meteorologist to figure this out. Okay, so we look aloft. What this is a case, there's a classic bounded weak echo region. It's the mesocyclone aloft being projected down. So again, you notice in the inflow region, weak reflectivity. That's where a lot of this goofy velocity stuff is. It's a projection of side lobe from the real high reflectivity ring aloft where you have more believable velocities. And you notice it gets a smoother appearance as we go up. Now it's associated with the actual core of the storm. So this is a more believable signature. And the reason you have the CC min is just because it's not raining. There's not much precipitation in there. And then we continue aloft. And again, it looks most realistic in the highest elevations and less realistic as we go down. Okay, so the takeaways here, if you're looking at this, trying to apply this information, you know, you've got to remember that the tornado probabilities are a function of rotational velocity, how high above the ground is it, though that's a pretty weak signal. Circulation diameter is a much stronger signal, and you've got to have something to hit. And then the point is, maybe in the east or the Mississippi Valley, it's not as big a deal, but you get out into open areas like the Great Plains where you can vary wildly from, think of the El Reno tornado. That was, other than people in vehicles, it's winter wheat fields is most of what it is. But if you go 20 miles to the east of there, it's dense metropolitan area. And it can be a multi-billion-dollar difference and dozens, if not hundreds or thousands of injuries and fatalities depending on where it sits. So point is the weather event could be the same, and you don't always know all the details about who's in the way, and it's probably not good to assume that you know who's in the way. People camping, there's all kinds of things that can be going on that you're not going to know about. Point here is we're trying to encourage you to approach as a meteorologist. You know, you're not necessarily a social scientist, and you're not responsible for the way people behave, but the point is you can at least get the best information possible out there about what the meteorological threat looks like. And then again, all of this is contingent upon quality interpretation of quality velocity data. If you don't have that, you can easily come to the wrong conclusion, and people do it all the time. And so I'm just hoping that 5-10 years from now, those of you who are doing this sort of thing professionally, that I'm not sitting in SPC, shaking my fist, looking at the radar, somebody's got a tornado emergency for a false debris signature, a fake mesocyclone, that sort of thing. Just, you know, it all comes down to our credibility as a whole. So the better job you can do, the more credibility you maintain and the whole enterprise maintains. And that's it.